So far, I briefly introduced how a grating works and why the line density is so important. Today, we discuss how to select the optimal grating. To understand how to choose the optimal grating, we must go back and look at the typical Raman spectrum once more. Here, the spectral range from 100 to 2000 wave number is considered as a fingerprint region. It contains the most important information of molecular vibration, which is needed to identify sample. Additionally, most organic substances have a group of strong peaks around 3000 wave numbers, presenting the CH and NH stretching bands. They are less distinctive, but nevertheless also quite useful. Therefore, 100 to 3500 wave number is considered as the full range of Raman effect, and the molecular vibration with an even higher vibration frequency is rare. Now, let's come back to the grating. Basically, if you want to have full Raman range projected on CCD, you must use a grating with a lower line density and weaker dispersive effect. But if you want to inspect small spectral range and resolve more details, you select a grating with a higher line density and a stronger dispersive effect. The dispersive angle of a grating is wavelength dependent, but in Raman spectroscopy we use wave number instead of wavelength. With a change in the laser wavelength, the dispersive angle needed from a grating also changes. For instance, if we use a laser of 450 nanometer, the fingerprint region is 43 nanometer wide. But if the laser is 800 nanometer, the fingerprint region becomes 146 nanometer wide and needs a grating with a different line density. As a result, to achieve various spectral resolution with various lasers, we will need multiple gratings and must switch among them. This brings two new challenges: changing the grating and calibrating the spectrometer. In the next two videos, we will see how a modern Raman spectrometer handles these challenges.